afternoon. Hopefully everyone enjoyed lunch and didn't eat too much so that you can make it through the afternoon. Next, we're going to have our session on battery storage. And the two folks that are going to be presenting are Jeff Lerner. He's the Manager of Forecasting Operations with Vaisala. And our very own Allison Weis with Ascend Analytics. She's our Director of Optimization Analytics. She's the brain trust behind Battery Sim, which I'm sure is why all of you are here ultimately. So, Jeff?
Thank you, Scott. So I'm the surprise presentation today. If you look in your agenda there, you won't see this presentation, but this fits very well into this session since I'm going to be talking about renewable energy generation forecasting. So a little bit different than what we've been hearing. I'm actually an atmospheric scientist by background, and I lead a team that we make the wind and the solar energy forecast, and we also do hydro stream flow forecasting. So a little bit different than what you've been hearing, and hopefully you get some of the acronyms that I'm going to be presenting. All right, I'll talk a little bit about the current state of the art in the renewable energy forecasting. What are the importance of observations to the short and medium term forecasting? And the solar versus wind accuracy metrics. So the question that I posed at the beginning of the first slide, is it harder to forecast for clouds than it is for winds? And there's some intuitive and non-intuitive results that I'll be presenting. And then also opportunities for improving these kind of forecasts. Okay, this is just a picture of some observations from a solar plant at the top. In the bottom, those observations and forecasts from a wind plant. These are 1 minutely observations, and then the forecasts are at 1 hourly granularity. So typically, most consumers will get the 1 hourly granularity forecast, but you can see, obviously, it will be represented differently because of the variability. And most of these day-ahead, I'm going to be talking mostly about day-ahead forecasting, are using these numerical weather prediction models. These are the four-dimensional models that a lot of the forecasts that you see in the media, they're based on that. And they're very complex. They have all the physics and dynamics of the atmosphere, and I'll be talking a little bit about that. Now, the ramp rates are very variable. So the one at the top here is a plant, I believe this is a site that's, I'm sorry, this is a radiance at the top, I apologize. And this is from Boulder. So this is a pyranometer that's located nearby here. And you can just see this is like a May afternoon. And you can just see in the afternoon, and this occurs almost every afternoon in May, you just have these kind of air mass clouds that you get all this kind of wild variability. So you can see that the model's not going to pick that up because it's at hourly resolution, but when you start averaging those obs at hourly, they're going to kind of line up a little better. The bottom here is a wind plant that is in the Northwest, and this is minutely data, and it shows as well there's a lot of these small-scale wind events that happen that the models oftentimes don't pick up on. And that gray band there, that's the area of the power curve in the transformation where you have the steepest part of the power curve. So small errors there are going to translate to very large errors in power. And I'm just showing wind speed right here. Okay. And one other thing to point out that's pretty important is that during the warm season, this is where these weather models that form the basis of these day-ahead forecasts, this is where they struggle because there are a lot of small-scale things that happen in the atmosphere that aren't picked up by these numerical weather prediction models. So if you think of thunderstorms, for example, getting the exact position and the magnitude of these thunderstorms is pretty important, and that can affect the winds that you get out of your generator. So getting those forecasts correct is much harder to do. You have to go to a higher resolution. Even there, you're not guaranteed you're going to get some of these kind of thunderstorms. And similarly with solar, if you can imagine, even looking outside today at lunch, and you look at some of these clouds, they're at very fine scale, less than 5 kilometers, even some of them less than 1 kilometer. And so to resolve those kind of clouds and when it's going to become sunny and how it's going to affect the solar plant is pretty tricky, as you might imagine. Okay. Who are we to talk about this? Vaisala has a lot of experience forecasting throughout the world. The colored blue areas are areas that we either currently forecasting for or have forecasted for in the past. A little bit about Vaisala. We were 3-tier previously. 3-tier was acquired by Vaisala. Vaisala makes weather instruments and environmental measurement and also services. So I'm in part of the services team in Seattle, and we do a lot of resource assessment and operational forecasting. And we've been doing it since about 2001. Yeah, and so we're in the Seattle office, we're focused mostly on that, the resource and getting that right. We actually have an office here in Louisville. People are familiar with the area, but they're manufacturing instruments. This is really good schematic to kind of understand when you're doing renewable energy forecasting, what are the most important predictors that you use to forecast power, okay? So at these different scales, and we're looking at from 0, from now until a year ahead, you have different main predictors that help you forecast what the power is going to do. So I'm mostly talking about within a week here. So most of the markets we're talking about, day ahead, some of them balance a day or even shorter term. But really, observations are the most important predictors when you're talking about very short-term forecasts, hour ahead, 2 hours ahead, 3 hours ahead. And those observations could be from a SCADA system, like at a wind farm, could be from a solar plant. You're talking about getting irradiance measurements. Satellite data can be important, depending on the time scale. And then once you get beyond about 4 hours, then these numerical weather models are really important because that has the full physics and dynamics of the atmosphere, and really the observations fall apart as important predictors of what's going to happen like tomorrow, let's say. And then when you get further out, then you start talking about climate signals. And I'm not going to discuss that today, but we actually do make forecasts at that scale, but you're not talking about hourly forecasts. You start getting to like weeks or month granularity. And then at the bottom there are some of the applications of these very short-term forecasts, which you can recognize just from your what you're probably involved with in planning. Okay, this is a flow diagram of what a typical or state-of-the-art forecast system might look like. So there are inputs on the left that go into the numerical weather prediction model and the advanced statistical model. So if we just use those weather models by themselves, they aren't going to capture local conditions. So you can just tell by, look at Tehachapi or look here in Boulder, and the mountains are going to have a profound impact on what's going on locally. So these weather models, they typically have a resolution of about 10 kilometers in a grid point, horizontal grid point spacing. At that resolution, some things you aren't going to capture. So there's going to be inherent bias in those forecasts. And that's where these advanced statistical models come into play. Don't know if we have a pointer here. Don't think so. Oh, yeah, there we go. So what I want to point out is that just taking the numerical weather prediction model, you have some inherent bias. That's where these statistical models come in, where the real-time SCADA or historical observations are really beneficial to lowering the error in the forecast. And so that comes into the statistical models, and you get an hours ahead power forecast. And you can also use that historical data when you're applying it to the numerical weather prediction output. And then you can get a day and week ahead. And when you combine these two, you'll have a forecast from like 1 hour to 1 week ahead. So it's pretty powerful when you use the two in combination. If you just use one or the other, they might not perform well either in the short term or out days ahead. Okay, talk a little bit about importance of observations, because if you don't have any observations, you're kind of flying blind. You don't have ability to validate in real time. You don't have ability to take those recent observations and recalibrate your models or retrain your models. So the point of this slide is to show that what I did here was I show the forecast horizon in hours on the x-axis, and on the y-axis is the mean absolute percent error. And what I'm trying to show here is if you just use persistence and you have an observation and you just said, okay, that's my forecast for the next few hours, this is what happens to your error. So close to now, it's going to be really good as a definition of persistence. But as soon as you get out beyond about an hour or 2 hours, it really degrades. Now, using that system where I showed you the flow diagram in the previous slide, we can do this orange line here, and that's just using historical observations. But when we have real-time observations, we can even do better than persistence. So that green line here is showing the optimized forecast where you can improve upon just using persistence by using machine learning algorithms where you have different predictors that go into your algorithm. So it could be from the weather model, it could be the observations from on site, and it could be lagged observations as well. Because if you want to catch the ramp, you want to have some kind of information on what recently happened, right? So that's what this is showing here, is we can improve upon just using persistence. But let's say you didn't have any observations versus having observations. Back of the envelope calculation here is if you took a typical size wind plant, 100 megawatts, let's say with a net capacity factor of 30%, the actual volume you save by going with a more accurate forecast, it comes out to about 6.1 gigawatt hours per year. That's at a 1.5 hour horizon. So it's pretty profound when you talk about over time the amount of energy volume that you're actually saving by having a more accurate forecast. So getting to the answer to the question, what's easier to forecast, clouds or winds? What I'm showing here is I picked a couple plants, wind plant that was about 100 megawatts, and I also picked a solar plant that was about 100 megawatts in the desert Southwest. And then I picked a mid-Atlantic solar plant that's in PJM that we're forecasting for. And I looked at last 2 years of data, and I picked out all the clear days and the cloudy hours and the clear hours. And what we're seeing here is that for the wind statistics, there's almost no bias. The mean absolute percent error is about 14 and 19. And first I want to comment, I didn't really do any deep QC here. I just took the data and I said, okay, I want to see what my results are going to be. So there's probably going to be a certain amount of outages in here, but not much at these sites, but there are some outages. And for the mid-Atlantic site, there's some snow on a few days. But what I wanted to show is just when you isolate out what cloudy is, and I used a less than 80% of the clear sky. So anything less than that, I said that's cloudy. We got some interesting results. The bias is enormous, and so are the errors at this solar site in the Southwest. And that's kind of like counterintuitive. It's like, well, it's usually, this is a site where, why would we be so high bias? Well, it's a rare event. If you look at the number of hours or the percent of hours, it's 12% of the time where you have actual cloud conditions by that definition. But when you look at all hours, which is in parentheses, the bias, the MAP, and the root mean square is much lower. That's still high, I would argue. And so there were some other things I saw in the data that could explain that. What is really interesting, though, is you take a cloudier site that's 58% of the time cloudy hours, and this happens to be in New Jersey. And what we're seeing is the error on the order of 12 and 18% for the MAE and the RMSE. And then when you take all the hours, it's not much different. So there's so many hours that are cloudy. But the bias is still high. So what this is pointing to is you have rare events of cloudiness, of course, in the Southwest. And so you have to do you have to have more training data so that you can train your models to target those periods of time where you have those big errors. And these happen in mostly like July, August, September for this particular location in the Southwest where they do have the monsoon. So pretty interesting, kind of a little bit counterintuitive. We're able to forecast the solar better in the mid-Atlantic where we have a lot of training data that has clouds in it, okay? Other thing was interesting to note is the wind and the solar then are about equally easy to predict, you could say, or hard to predict when you have a cloudy site. When it's a site where it's a rare event to get clouds, then it's actually an inferior forecast performance. Okay. And just some samples of these busts. The top graph here is showing, this is the tracking site that's in the desert Southwest, and it shows some of these busts where you can see you just miss the the clouds that day. And then here's another period of time where you had some indication there might be some clouds, but look at how much it was missed. So I'm just showing the bad stuff here. And then this is interesting. This is the Mid-Atlantic site. So even though this, some people consider a bust based on the percent error, you would get a good indication that, hey, I'm going to be really cloudy this day, even though you had some pretty big errors. Your forecast was saying, you know what, there's much reduced capacity, because this is 0 to 100% of the capacity on the y-axis. And then here's showing another event where you can see the variability and where there were some big misses. And again, this is like 10-minute data and 1 hourly forecasts. So just want to give you some like samples to see, so you can see what that looks like. So in conclusion, though, here are some opportunities where we can improve on these day-ahead forecasts that feed into decision support tools like we're going to hear about in a minute here. Using a regime or climate-specific model training algorithms. So like I was saying, if you don't have a lot in your sample of rare events, it's going to be much harder to forecast. But as far as you start accumulating this data, then you can actually get better trained models. There's also these ensembles of these weather models that are becoming more prevalent. So these are these weather models that are run multiple instances, so you can get like a better envelope and probability distribution of what your forecast will be for the cloudiness or for winds. Also, if you're aggregating geographically diverse plants, that also tends to lower the errors. And improvements in modeling atmospheric boundary layer. Right now we're involved with a project for a DOE-funded project on improving the solar forecast from a model called the Weather Research and Forecast Model. And we're really trying to address certain clouds that are in the boundary layer and getting aerosols into the model so that we can forecast these clouds and reduced irradiance events better. And then also the compute power we've been really taking advantage of. The Weather Service just made a big upgrade to one of their models where they're actually going to be able to now improve the resolution because they got a big plus up in Superstorm Sandy funds to improve their supercomputers. So that would definitely translate to improved forecast resolution and being able to resolve some of these smaller scale features better. So, and there's also a lot of open source software that you can get for data mining and advanced methods, statistical methods. So it's pretty promising time. All right, I'm going to hand it over next to Allison. I don't know if we have enough time for questions or if we're going to hold off till after your session.
I'll take a couple questions now. People have them.
Okay. Yes.
So, just quickly wondering, it seemed like all of the production forecasting and observations were done on an AC basis.
Mm-hmm.
Is that correct?
Yes.
So there are underlying factors, DC-AC ratios, that were going to impact that. But I'm curious what your comments would be on the forecast. I assume that the forecast is built upon AC level information in production versus DC side production information. And if you had a DC side data set, if that would or should increase your forecast or reduce your forecast error.
The models that we're using are kind of agnostic to what it is that you're feeding it. I mean, you can give it DC or AC, or you can even give it anything related to the weather, and it will just, you just have to have like a nice history of your target variable. So we've actually had a couple sites where they've given us DC data, and we're actually just training it the same as we would AC. So it's somewhat agnostic to what it is, as long as it's correlated to weather variables that are predictors for your target variable. Question in the back, yes.
In the CSP industry a number of years ago, cloud forecasting algorithms were being included in ground-mounted fisheye cameras pointing towards the sky. Have those been outpaced by improvements in satellite data?
Those actually serve a certain time scale the best. So those like fisheye, that technology, I was just talking to someone at lunch about that, but those are really expensive when they initially came out with those sky imagers. Now you can get cameras that have fisheye cameras, cameras, you can get cell phones that have them. So that technology is actually becoming much more affordable, but that really only helps you in about the first 30 to 40 minutes, and then it's really out of view, your field of view. But it is serve a purpose for that. So if you can think of like high frequency markets, that definitely has a place. Satellite really comes in when you're talking about 30 minutes out to about 2 to 4 hours. And then your assumptions about cloud motions kind of fall apart. And so they have different horizons that they're better at. And then once you get beyond that 6 hours, then you rely on these weather models. So when I was talking day ahead, I was mostly focused on these weather models. But there's actually these new weather models that actually update every hour. And those are kind of exciting. There's one model called the HRRR, and that assimilates satellite and radar data, so you can get these thunderstorms a little better in the short term. So that's another promising technology. Okay, thank you.
Great. Thanks, Jeff. So that forecasting is definitely a key input for the next piece of analytics that I'm going to talk about today, which is our day ahead and real-time bidding analytics for batteries. Great. So what we're working on is a set of analytics to create day ahead and real-time bids, both for standalone storage paired with renewables. This can also be applied to renewables only, looking at committing into day ahead versus real time, which I'll show a little bit on the next screen, but focused here on the batteries first. What we're going to do with the forecasts from Jeff's software, as well as forecasts from the ISO that give us the load that they expect for the next day, the renewables across the system, as well as any outage information or other data about the system that they publish, normally about an hour before the day ahead bids are due. We take that and we feed that into our forecasting models to look at both, along with the previous price data from the different time series that we're interested in, into our models to look at what the expected level of prices are going to be for day ahead products, hourly products, so for regulation, up and down, and spin and energy, and then what the probability of price spikes are going to be in the real-time market for different threshold levels in different hours of the next day. So we're never going to be able to predict for 2:05 tomorrow versus 2:10 which of those is going to be higher when we're looking at like 9 to 10 a.m. on the day before. But we're trying to understand, based on the status of the system and where we are going to be in the supply stack, what kind of outages are present, and how inaccurate some of these system-wide renewable level forecasts are going to be, what the probability of having a lot of volatility in real time is going to be. And that's going to mean that it's going to be more profitable for the battery system to wait to participate in real-time energy versus being physically committed into a day-ahead regulation product. And so this square box here in the dark blue on the left is going to be that optimization across the window of the next day for which hours you want to be in regulation versus bidding into spin, where you're going to, in CAISO, have the opportunity for bidding into real-time energy, or in other markets, you just want to leave that hour open for real-time energy participation. And so that information then goes off to the ISO, and settlements come back, and we're going to update our forecast of what the probability of price spikes are going to be in the upcoming hours, and then combined with the information about what we're committed to in the regulation market in future hours and in the spin market, so that we can maintain the necessary state of charge buffers in the battery for participation in those markets. We're going to make a bidding decision. This is also going to pull in the latest information from the EMS system, from the battery on site, to know what our state of charge is, at least what it is at 75 minutes before the market period when the bids are due. And so there's still some uncertainty about what your state of charge is going to wind up at once all of that real-time hour has cleared. So based on all of this information, we're going to set a buy and sell price into real time. That gets submitted to the ISO. And they're going to come back with real-time dispatch instructions straight into the hardware of the system. Depending on the risk tolerance and what you want to do in the market, there's also can be the opportunity for either a little bit of additional revenue or some protection against regulation signals that are unfavorable of following some of the real-time price dynamics instead of the AGC signal, if that's within sort of the performance standards that are allowed for that ISO for operations. So we can also do sort of a similar analysis for a solar system, although it's a lot simpler because we're not tied through time about what the state of charge of the system is in 1 hour, affecting what you can do in future hours. Instead, we're really just concerned with, based on what forecast we have of generation day ahead for the specific site, whether or not we want to bid all of that into day ahead or some fraction of it into day ahead and settle the rest in real time. And so to do, given the new price dynamics of these price spikes in the real-time market, we need to do the same forecasting of the probability of price spikes. The underlying, if you remove the price spikes, a lot of the underlying relationship between day ahead and real time is predictable and sort of by season and time of day. But once you add in the variability of when price spikes might occur, you can't see a regular pattern. So you need to do that same price spike forecasting as well for solar-only systems. But you're mostly just making a single day ahead decision about what you're going to, percent of your forecast you'd bid in. Everything else will then get generally automatically settled by the ISO in real time. So talking just a little bit more about the day ahead forecasting. Basically, we're trying to do, this is a chart, those of you who are in the battery workshop yesterday might recognize or have been using the software. In our valuation software, we do some simple rules about what we can forecast day ahead versus real time for participation in regulation versus waiting for these real-time energy opportunities. And in this operational software, what we're doing is making a specific forecast for the next day that improves upon that by using all of these predictors that we reviewed previously about the state of the system and the recent trends in the price data. And so this is going to give us a specific set of hours that are going to be better for the specific next day for participation in real-time energy. So we think by using this probabilistic forecast of what different price spike thresholds might occur in the next day is going to give us a lot more information for making these decisions about whether we should be in day ahead versus real time compared to just using some deterministic guess about what the day ahead real time spread might be in any given market hour for the next day. And yes, let's see. So we're really just trying to see what's going to be the greatest opportunity. I think that's for day ahead versus real time. So we're going to look at the probability of different levels of price spikes. And if the more likely that different, this is more things feed into the day ahead optimization than this simple decision hour by hour. It's just a visualization to get an idea of some of the core trade-offs that the analytics are making. So we're going to do more participation in energy if there's a higher probability of very profitable price spikes, which is the green down there, going for energy, versus if there's not going to be a lot of volatility in real time, depending on the expected level of ancillary prices and sort of the general state of charge optimization through the day, we're likely just going to want to stick with regulation. For the real-time bidding, we want to know as soon to when we have to bid as possible what the current state of charge of the battery is. There's a lot of uncertainty in exactly what the regulation signal might be in any given hour in some of these markets. Some markets like PJM and ISO New England have a very consistent balanced signal over a very short time horizon. In CAISO, that's not the case, and there may be certain periods that get more imbalanced than others. So we always maintain some buffer of state of charge in the battery to deal with those unexpected events that differ from what the mean expected movement might be on a signal. And then So we're going to take the most recent data that we have on where the battery state of charge has ended up before we have to submit the bid for the deadline of the given ISO. We're also going to take into account the time of the day and the time of the year. But there's also going to be information about what our future commitments are in day-ahead products that are in following hours that we also need to maintain certain SOC buffers for, as well as updated information about the price spike probability in the upcoming hours. All right, so we can take a look at some sort of sample results. So we can see here on the left we have just an example from 2 different days in August. So if you were doing just a rule by time of day and by time of year in the peak hours in the evening, you're going to probably want to be in real-time energy, but you can do some forecasting based on differences between these days that show that in the lower day you actually have a much less opportunity in real-time energy than in the upper day, and so you can make different decisions day ahead versus real-time. If we sort of average the results of the model across the whole year, this is not going to give us information about any specific bid, but we can see that this probability of price spikes follows sort of the expected shape of the duck curve for this CAISO node. So these are a couple cuts sort of into the resulting bidding function that gets trained for a given node for a real-time market operation, looking at it along some of the different axes. So we can look at what the buy versus sell price is for different states of charge. So the more full the battery is, the more willing we are to sell, and the less willing we are to buy, and vice versa. As we empty, we want to, the more likely we are to bid to buy versus sell. And then we see obviously the duck curve again, sort of effect of like peak load leading to spikes in evening hours and low prices from hydro in the spring, in the early part of the year. All right, so this is just showing sort of in the context of the valuation model that a lot of you saw in the workshop yesterday as well. So we talked in that workshop about the costless adders that we use in our valuation model. So we want to have that model be a conservative estimate of what you can do when we run it with the rules case, a conservative estimate of what you can do with this live operating software. And so we see on the far left the rule-based operation of the valuation software, which we then exceed with the live bidding software. And even further, if you do these sort of ISO overrides following price spikes, a very small number of the years. And let's see, I think we're almost out of time. So here's just a breakdown of the different revenue. So you submit one bid into real time, but it's going to get settled against 15 and 5, and so the revenue is going to come from both of those price streams for the CAISO market operation, along with participation in the various ancillary products. And there's a lot more opportunity for energy revenue in certain months of the year, as we would expect in the summer months, versus regulation being more sustaining revenue through other times of the year. All right, so I think we're about out of time, so I'll stop here and get any questions.
As there's a concentration of batteries in a specific market or zone, and potentially a concentration of batteries that are all using your dispatch methodology, how does that impact expected revenue if people are chasing the same spikes and using the same sort of switching strategies between revenue opportunities?
Yeah, so we definitely see regulation prices falling in many markets as they get saturated with batteries. That's a very narrow market that will get easily filled. The real-time energy market, we have a forecast of the volatility and how that comes into balance with battery systems that get added into this into an ISO. There is continuing mismatch between day-ahead and real-time as the renewables are being added even faster than the battery system still in all ISOs. And so that's not going to make a sudden drop in volatility, but there will be an eventual decline as battery systems begin to catch back up and come into long-run equilibrium with that. All right. Thanks.